Hello everybody, Dave here, and today I'm going to be talking about Avogadro's number. And in this video I'm also going to show you me drawing out Avogadro's number onto Rubik's Cubes. And then it's going to be in a 4x4, or 2x2 actually, so I have 4 Rubik's Cubes. And within that I'm going to be drawing out Avogadro's number. Now, so to give us some brief background, I suppose. In chemistry, you need to measure the amount of matter that you have, right? So one way of counting something you have, for example, could be by the kilogram, by pounds, by volume, gallons, etc. Or another example would be for eggs, you would use 1 dozen eggs, which means 12. And the same thing applies for Avogadro's number. As you can see here, I just finished the number 6 with my Rubik's Cubes, 6.02 times 10 to the 23rd of Avogadro's number. Now, if you have large quantities of something like eggs, right, it would be easier, or much easier, to count them in the dozens, right, instead of counting individual eggs. The same thing applies for Avogadro's number. If you want to count the amount of molecules in a specific amount of mass or volume, then you would use the mole or Avogadro's number to help you to find it easier. And just to clarify, Avogadro's number is spelled Avogadro, and not like avocado or something, even though it sounds pretty similar. I just want to say that. And furthermore, for the mole, it's spelled out M-O-L, not M-O-L-E, like the animal. Now, Avogadro's number can be very useful in other ways as well. In order to find the volume of an X amount of molecules, then you would first need to know that one molecule of represented particles at standard temperature and pressure occupies a volume of 22.4 liters. So, for example, if you have like approximately 2 moles of gas, then it would occupy about 44.8 liters. Avogadro's number is also useful because, for example, if you try to count each grain of sand in the beach, it would be really hard, but it would be easier to represent theoretically with Avogadro's number. Avogadro's number was named in honor of an Italian scientist named Amedeo Avogadro de Querigna. I might have butchered that a lot, but you could Google that for the correct pronunciation. And he helped to clarify the difference between the atoms and molecules. And we use the term representative particles whenever we talk about Avogadro's number, because a representative particle means the species present in a substance. For example, it could be like the atom or the molecule. As a general rule of thumb, in order to find the 1 mole of an atom of a specific element in the periodic table, you could just look up the element's the element's mass. So, for example, 1 mole of carbon atoms would be equivalent to 12 grams. Because according to the periodic table, carbon has a mass of 12. So that's just a general rule of thumb to follow. Also, if you want to find the mass mole of a compound, for example, sulfur trioxide, you would just add each molecule, or each atom. For example, in sulfur trioxide, you have 1 sulfur atom and 3 oxygen atoms. 1 sulfur atom is equivalent to 32.1-ish grams, and each oxygen is approximately 16 grams, and you have 3 of those, so you multiply 16 times 3 plus 32.1, and that gives you about 80.1 for 1 mole of 80.1 grams per 1 mole of sulfur trioxide.
Furthermore, if you wanted to find the mass in grams of 1.4 times 10 to the 23rd molecules of N2, you would first need to multiply 1.4 times 10 to the 23rd by the conversion factor. Now the conversion factor for this would be 1 mole over Avogadro's number, because we want to convert this into moles. Once we find out how many moles 1.4 times 10 to the 23rd molecules of N2 is, which is approximately 0.233, we multiply that by 1 mole of N2. And in order to find how much 1 mole of N2 is, we have to go get our periodic table and find how much nitrogen by itself is. So according to the periodic table, nitrogen has an atomic mass of 14 grams. Since we have 2 of nitrogen, we have to multiply 14 by 2 to get 28. So therefore, 1 mole of N2 is 28 grams. So now we multiply 0.233 moles by 28 grams over 1 mole to get 6.524 grams. So the mass of 1.4 times 10 to the 23rd molecules of N2 is 6.52 grams. Also, if we have approximately 124.7 liters of carbon dioxide, or CO2 as it's also known as, and we want to convert it into molecules, how many molecules it is, we first have to multiply 124.7 by the conversion factor. And the conversion factor here would be 1 mole over 22.4 liters. And we put the liters on the bottom so that the units would cancel out. This would give us about 5.56 moles. So now what we can do is we can multiply 5.56 moles by Avogadro's number, which is 6.02 times 10 to the 23rd. And as a result, we get 3.35 times 10 to the 24th molecules of CO2 in 124.7 liters of CO2.
And finally, you can see that I have just finished 6.02 times 10 to the 23rd on my Rubik's Cubes.